So we're given that s of t, and remember s of t is position. It behaves 3t squared minus 3e to the power t. So that's the position function. The question, what is the acceleration at time t equals 0? All right, so we have negative 3, 0, 3, 6, 9. A, B, C, D, or E. What's the answer? C. C is the correct answer. So, remember, there's relationships between position, velocity, and acceleration. Take the derivative of position, you get velocity. Take the derivative of velocity, you get acceleration. So we're really after the second derivative. So we take two derivatives, we're very careful, we make sure we apply our rules, and then we plug in 0. And life is good. Life is wonderful. Now, I will say that most of our rules, when we've been phrasing them, have oftentimes been in terms of x, like the derivative of x squared is 2x. Does it bother us that we changed it to t's? Does that matter? No. It's a symbol. Symbols can be changed. And so it's important to be adaptable. And indeed, a lot of the power of math is learning to say, oh, I can call this something else, but then I can use my similar ideas. All right. So there we go. There's our practice. May all our multiple choice problems be that reasonable. Now, last time we finished our how to prove things, I wanted to throw in a comment for today, for our start of today, which is to say that mathematics is built off of patterns. And it's important to be careful not to confuse coincidences with patterns. There's an example here. So you can imagine, you say, look, I have 16 divided by 64. So what do you do? Cancel the 6's, right? And you get 1/4. Well, is it true that 16 over 64 is a fourth? Yes. Is it true that that's the reason why? No, because you can write down pretty much any other fraction and it's not going to work, right? Like 19 over 95, cancel the 9's, you get what? 1/5, which, oh wait, that's actually true. Okay, but the moral is, it will not always work, okay? So this is a coincidence. And one of the big challenges that people have, and I think this is particularly pronounced in a Calc 1 course, is that you've seen so many different things, you've seen lots of interesting things happen, but you haven't yet sorted out what's coincidence, what's a pattern. In other words, well, this thing happened once, so I'm going to keep doing it again and again. But it only worked in that one case. So you have to make sure that you know. Now, how do you know? Well, essentially, a pattern is something that can be justified and explained. A coincidence is something that only happens in very unusual circumstances. So that's why we are very careful. We are explaining why things work. We're building up the tools so that we can justify it. So there aren't coincidences in what we say. We just have to learn. Now, I do want to say a little bit more about the philosophy. Why do we care about seeing patterns? Well, in some sense, you might feel like there's so much I have to learn. I feel like their knowledge is like this big balloon that's filling up. And I don't know if I have space to keep throwing things in there. But you see, here's the great thing, is as you gain knowledge, it's not just a matter of things getting more and more. You can also start to actually somehow compress. Compression comes from patterns. Saying, look, these 10 things here, they all follow one pattern. So instead of memorizing 10 things, I memorized the one pattern, and now I have less I have to keep track of. And so that's why it's really important to start to spot patterns, to learn patterns, and to use them. It makes it a lot more fun. A lot more fun. All right, so there's our thought for the day. Now, on to today. And our goal for today is trigonometric functions. And before we jump in, I just want to talk about trigonometric functions. So goal is trig derivatives. All right, that's our goal. But I want to stop and ask a question. Why? Why do we care about trig derivatives? Now, why should we care about trig functions at all? And if you were taking the business calculus class, you wouldn't. They don't even talk about trig functions, those poor souls. So why do we care? And I want to mention this because I think there's some really beautiful things that go on. So in essence, if you think about trigonometry, and I will tell you some biases, I like trigonometry. In high school, that was the first time math clicked for me. I got, I think it was a C or a D in algebra. Did terrible. But boy, did I love trig. And it was my first class I taught. But okay, I'm sorry, I'm waxing, remembering the good old days. So why? Well, if you think about trig, there's sort of two versions of trig. There's trig with triangles, and that says, look, we care about things where we have like right triangles. And this gets back into, if you think about what trigonometry is. If I could spell trigonometry. So trigonometry. Now the first part, great, that's triangle. What's this last part? Metry. What is that about? So triangle, what? What is metry doing? Measuring. So trigonometry is about measuring triangles. And it turns out that when it comes to measuring the world around us, that triangles are the ideal tools. And so a lot of the instruments that we use to understand the world is through the language of trigonometry. It's through that way of measuring angles. And so this is important to us because this helps us measure the world around us. And a lot of things are built off of angles. So that's one of the reasons. Now, there's another version of trigonometry which is more along the lines of circles. And these are the trig functions which you probably think of as just going on forever and ever. Now, why do we care about these types of functions? Well, this simple idea is these capture periodic behavior. And a lot of natural and even some unnatural phenomena, I guess, can follow or will follow periodic behavior. So, for example, if you want to measure things like the tides coming in and going out, they're periodic. When you look at sound waves, they look like sines and cosines that have been stacked on top of each other. Anything which has this sort of periodicity built in naturally ties back to sines and cosines. And if we want to understand these structures, we need to understand what's going on with them, and in particular, what's going on with them with calculus and their derivatives. So there are important reasons for us to want to study the trigonometric derivatives. So, okay, so that was our aside. All right, so our goal for today, the derivatives of our basic trig functions. So there's an ingredient list I prepared. These are the things that we're going to need to put our derivatives of trig functions all together. And some of these will look very familiar. Some of them maybe not so much. So let's talk about the ones which we know hopefully very well. The definition of the derivative. Do we know that? We're good with that? Yes. Maybe. But okay. Well, we'll study it by the time the exam comes around. Sine x over x, classic limit. We talked about how we use the squeeze to get that one. Now this other one, cosine x minus 1 over x, we didn't quite do that one, so let's go ahead and do that one because, you know, it's part of our ingredient list. Now, there are sort of two options, which is, one is we could try to figure out something starting from scratch, or two is, let's use what we know. I prefer to, let's use what we know. What do we know that looks vaguely like cosine x minus 1 over x? Is there anything that vaguely looks like cosine x minus 1 over x? Anything at all that jumps out to you that we could maybe appeal back to? Oh yeah, sine x over x kind of has that same flavor, right? Trig upstairs, x downstairs. So we say, cool. So we start thinking, is there a way? Is there any possible way to connect back? Well, we put on our trig hats. Now, the nice thing about trig, and maybe it's one of the hard things about trig, there's a lot of identities. And so that literally lets you say, there's lots of ways to write things. Is there a nice identity that involves both sines and cosines? One that perhaps we have tattooed on our hearts because it's our favorite identity. Sine squared x plus cosine squared x equals 1. Beautiful. Beautiful. Now, we don't have cosine squared x, we have cosine x. So what are we going to do? We're going to find a way to square it. Now, you're probably thinking, well, you can't just square it, can you? No, we can't. But we have technology. So, how can we make something squared? Think back. For example, how did you get rid of square roots? You squared it. What did you do?
Multiply by itself.
Well, not multiply by itself.
Exact opposite.
Well, what do you mean by exact opposite? The conjugate. So multiply top and bottom by 1. This doesn't change the expression. I mean, it doesn't change the value. We're just writing it in a different way. Okay, so upstairs, this becomes cosine squared x minus 1. Downstairs, we have x times cosine of x plus 1. We're not going to distribute the downstairs because it's the upstairs that's important. So you only do the distribution where it's important, where it's useful. You don't do it where it's not useful. That's a pretty good rule of thumb. Do things where they're useful. Pro tip, be good, be useful. All right, x goes to 0. So cosine squared x minus 1 becomes negative sine squared x over x cosine x plus 1. Okay, well, I claim that we can write that as sine of x over x times negative sine of x over cosine of x plus 1. So just sort of split it into something that we know and everything else. Now, the first part, sine x over x, what does that do? Goes to 1. What happens to this? Well, when in doubt, what do? First thing is plug in. You only do more work if you have to. When you plug in 0, what do you get? Upstairs, you get negative 0. Downstairs, you get 2. And 0 over 2 means 0. 0 over 0 means more work. 0 over something non-zero is like, woohoo, we're done. Okay, so we get we get positive 1 and 0. Multiply those together, we get our answer, which is 0. So, okay, so there's the justification for that limit. Down at the bottom, we have the quotient rule. We've talked about that before, so I think that's good to go. And the last two pieces are trig identities. Sine of a plus b is sine a cosine b plus sine b cosine a. And cosine a plus b is cosine a cosine b minus sine a sine b. So I could just say these come from trig, or I can sort of give you sort of a little bit of a motivation for why this might be true. Do you want to see some motivation for why this might be true? Or you're like, yeah, I'm good. Motivation. Okay. All right. All right. So I'm going to make some triangles. I'm going to think of these as angles. So let's start here. We'll make a triangle. And we'll put angle A here in the corner. And then I'm going to stack on that another triangle where this has angle B in the corner. So far, so good? No surprises? Okay, the moment of truth. Let's come up here. I claim that there's a triangle here. That's true. What's this angle? This one here. Channel your inner Canadian. Oh yeah, eh? You betcha, eh? Now, why is it A? Well, if you look here, you have 180 degrees. But you also have a 90 degrees taken out, which means that these two angles have to add up to a 90-degree angle. Or in other words, they're called complements of each other. They're complementary. Well, hello, A. You're looking great. Well, thank you. Have you lost weight? No. But, all right, they're complementary angles. What else are complementary angles? These angles are complementary. They have to add up to 90. So if these both add up to 90 and these both add up to 90, the only way that can work is if these two angles were the same. All right. Now, one other quick fact I'm going to put over here. And let's suppose I put theta here and L is the length. How long is the adjacent side of this triangle? It's L cosine theta. And how long is the opposite side? L sine theta. Now you might say, how do you get that? Well, sine theta is opposite over hypotenuse. And then you can solve for how long that has to be. So let's make this length 1. Because I haven't put any lengths in. What is this length? Hypotenuse is 1. Angle is B. This would be cosine of B. So I'll write that as C of B, just because I'm short on space. What's this length? S of B. Okay, now we'll come up to this triangle. I have A in this corner. This is my adjacent side. What's this length? Well, it's the hypotenuse, which is the sine of B, times the cosine of the angle A. What's the length over here? Hypotenuse times sine of A. Okay, this triangle downstairs. The length of the very bottom edge, what do we have? So the hypotenuse times the cosine of the angle. And this last piece, hypotenuse, sine of your angle. So far, so good? Now, the big, there's a triangle here. What's the angle in the corner? This angle is the sum of the two angles. So this length has to be the cosine of A plus B. Well, take the long length here, subtract the short length there. Cosine A, cosine B, that's the long length down here. Subtract sine A, sine B. So that's this length. This side, that's opposite a plus b. So this is the sine of a plus b. How do we get that? We add these two together. Sine a cosine b, sine b cosine a. And there we go. Trig is fun. What? That's so cool. Okay, all right. That was fun. Okay, so are we ready? Let's do sine. We have all our pieces, our ingredient list. We understand how it all works. We've seen this all. So here we go. You don't have to remember the individual steps. The individual steps are the justification. What you do need to know is the punchline. So the punchline is, if you're taking the derivative of sine, it's cosine. So we'll walk through the steps. So the first step is to say, I'm taking the derivative of something. So plug that into your derivative machinery. Derivative machinery, limit as h goes to 0, f of x plus h minus f of x over h. In our case, the function is the sine function. So sine of x plus h minus sine of x over h. Then we say, hey, sine of x plus h, that's like sine a plus b. So we apply our trig formula. And now why do we want to do it? Well, we want to sort of make a more apples to apples comparisons. We'd like it to have like sine of x's if possible. So applying our trig formula, the sine of x plus h expands out. Say, all right, well, good. Now what we'll do is we'll gather. Two terms have the sine of x. So we'll pull them to the front. There's a sine of x coming from these two places. One of them is attached to cosine h. The other is attached to minus 1. So there's sine of x times cosine h minus 1 over h. The last term has a single cosine of x, and then there's sine of h over h. Well, we know these limits. Cosine h minus 1 over h goes to 0. So this goes to 0 times sine of x. Sine of h over h goes to 1, so it's 1 times cosine of x. So the output is cosine of x. So the derivative of sine is cosine. That's nice. Ah, beautiful, beautiful. Mwah. All right. Well, how about cosine? Surely that's going to be just as nice. Well, let's find out. Same procedure. We're after derivative of cosine, plug it into the derivative machinery. You have a cosine x plus h. We have formulas that lets us rewrite that. So we rewrite it. And we say, okay, that's cosine x cosine h minus sine x sine h. Then we gather. There's a couple of cosine x terms times cosine h minus 1 over h. Then there's a sine x with the minus sine. Sine h over h. Again, the first part goes away. The second part goes to minus sine of x. Oh my goodness. This minus sign right here. So many students have lost so many points off of that minus sign. It's one of the biggest things that students can make a mistake on. So you have to be careful. The derivative of sine is positive cosine. The derivative of cosine, negative sine. So don't forget the minus. All right, so there we go. We have our basic facts. Nice, yes?
Do we have to do all of this when it's like if we're showing our work on a problem?
No.
Okay, thank God.
No. The goal, remember we talked about this a few days ago. Our goal here is we don't want to do this. Our goal is to get rid of doing limits. And we're doing that as fast as we can. But what we have to do is we have to build up a collection. There's two things that we have to collect. One thing we have to collect are rules for building blocks, our basic functions. So we talked about x to the power k, we talked about e to the x, we talked about a constant. So today we're adding more building blocks. We're adding the trig functions in, the sines, your cosines, your secant, your tangents. The other thing, of course, is how things fit together. And like, take a product, take a quotient. And so anyways, the goal for today is to add more rules for blocks. The goal for next time is to add one more rule, the best rule. one rule to rule them all. So, but that's next time.
Wait, so the derivative of cosine is negative sines,
Yes.
and the derivative of sine is negative cosine.
Yes. Okay, good. All right, we there's a conversion. I believe. All right. So, here's a problem. F of x is sine of x. Find the 137th derivative of x. Okay, so for reference, just because we're new at this, we'll write down some facts. The derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, that's for reference. Now, you might be thinking, are we really going to take 137 derivatives? I hope not. But don't worry, I brought paper. There's plenty of paper. Remember, it grows on trees. So it's a renewable resource. So should we need it, we can make it. But I'm optimistic something's going to happen. All right, so let's just start. So this is that kind of problem where it looks so intimidating, it kind of scares you away from starting. And so you say, look, I'm not going to jump straight to the 137th. Let's start looking and seeing if there's patterns. Start with small cases. And oftentimes small cases will give insight. So let's start with f prime. What's the derivative of sine? Cosine. What's f double prime? Negative sine, right? So the second derivative is the derivative of the first derivative. So you just take the derivative of the one above it. What's f triple prime? Well, let's go ahead and start using our notation. For third derivative, we'll put a 3 upstairs with parentheses around it. What's the third derivative? Negative cosine. Yes? Because the negative is acting like a constant. So when you see a negative, it's really shorthand for negative 1 times this function. And when we take the derivative of a constant times a function, the constant basically stays in front. And you say, we'll take the derivative of the sine. So it becomes negative 1 times the derivative of sine, which is cosine. Okay. All right. What's the next one? Fourth derivative. Sine, right? So it's like negative of negative sine, which turns it into positive sine. So this became negative sine of x. And in math, 2 negatives make a positive. Okay. Have we seen sine before? Just like our original function, right? After we took 4 derivatives, what happened? We got back to where we started. So it seems like something's going to happen. So like if you take the 5th derivative, what's going to happen? Cosine. It's going to be the same as the first derivative. And how about the 6th derivative? What will happen? The same as the 2nd derivative. Okay, how about the 7th derivative? Be like the 3rd derivative. It'll be like negative cosine. So they say, so we're like, it repeats every 4. So we have an idea. So instead of adding to our list, we think about the number 137. Okay, and we think about, how can we write 137? Well, I don't know. There's probably lots of ways to write it. I probably chose a bad number. Well, this is like 100 plus 36 plus 1, right? I can do that. The reason I'm doing that is like, well, 100 is 4 times 25. 36 is 4 times 9, and then plus 1. So what am I caring about with this one student? Why am I talking about 4 times? What's the punchline? Like every time I add 4, I get back to where I started. So essentially, if I do 100 derivatives, where am I? Back to where we started. If I do 36 derivatives, where are we? It's back to where you started. So we say, okay, so that tells us that doing 137 derivatives is going to be the same answer as if we just did a single derivative. So what's our answer? So our answer is cosine. So this tells us, aha. It's like we only need one derivative. All right, so that's the idea. That's the idea. Okay, so patterns. So I think I'm allowed to tell you this because it's no longer on the exam. One of the exam problems, remember I said we took one off, you could actually do right now. This problem is not on the exam. just for clarity. Find the 162nd derivative evaluated at 0 for f of x equals e to the x cosine x. Now we're not going to do this problem because we took it off the exam and there's a reason we don't want to do it. But how would you start such a problem?
Take the first few derivatives and see if there's a pattern that jumps out at you?
Yes, exactly. You take the first couple of derivatives and you look for a pattern. And it turns out that there is a pattern. So for instance, if you take the derivative, let me look at this for just a second. If you take the derivative 4 times, what do you have? So the fourth derivative, does anybody see it? Right, it's negative 4 e to the x cosine of x. And you're probably like, what? Okay, well, if we have time, we can talk about this one later. But let's do something else, though. We'll come back to that if we have time. I know, you're probably thinking like, you should have left it on. I would have aced that one. Okay. So here's a problem. d squared dx squared. Now, notation, what does this mean? d squared dx squared. Good, second derivative. So second derivative, x squared sine of x plus 2x cosine of x minus 2 sine of x. Does anybody have two terms? Okay, how about? Negative x squared sine x plus 2x. So, okay, so that looks some more similar to what I have. Good. Okay. Whew. All right, I was worried. I make mistakes, so sometimes. Okay, so second derivative. If you want the second derivative, what do you need to do? Find the first derivative. Okay, so this looks bad. And you're like, oh, it's going to get worse. And it kind of does, because you have to do your product rules. So you have two product rules. You know, derivative of the first times the second, first times derivative of the second. You go through. But then you look at it and you say, hey, I think this simplifies. Now, there's a comment here, a pro tip. It says you should simplify if and when it will help you in the next step. You shouldn't always simplify, but you should say, look, if it helps me do something, simplify. So if you say, I have to take another derivative, it's like, let me make this as simple as possible. So that's why there's motivation for us to simplify. So we get cancellation, and it turns out there's some collapse. So just down to x squared cosine of x. Now take the derivative again, product rule. Derivative of the first times the second plus the first times the derivative of the second. All right, good. Now, we did sine, we did cosine. What other trig functions should we talk about? Secant and tangent. Okay, so I'm not going to say much about that other than we don't have to go back to limits because we know things about secant and tangent. Tangent is sine over cosine. So if I want to take the derivative of tangent, it's the derivative of sine over cosine. Well, why do we do that? Because we have a rule, the quotient rule. Bottom times the root of the top minus the top times the root of the bottom, all over the bottom squared. Upstairs is cosine squared plus sine squared, which is 1. So you get 1 over cosine squared, and that's secant squared. So the derivative of tangent is secant squared. Derivative of secant, well again, say, hey, let's put it in terms of sines and cosines. 1 over cosine. You can apply the quotient rule or the reciprocal rule. And you say, that becomes sine of x over cosine squared of x. Well, which is sine of x over cosine x and 1 over cosine x. So that 1 over cosine is a secant. The sine over cosine is a tangent. So the derivative of secant is secant tangent. So there are 4 trig derivatives that you should absolutely know by heart. You're going to keep using these again and again and again. Over and over. So derivative of sine is positive cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of secant is secant tangent. These are very important rules. We'll put stars next to them. Now you might say, but wait, what about the other trig functions? Well, we can write it down, but to be honest, we don't like those ones as much. And you might say, why not? Well, they're very similar. So the derivative of tangent is secant squared. The derivative of cotangent, same argument, is negative cosecant squared. If you had to choose between these two, which one would you lean towards and why? Tangent. Why? There's no negative. Negative signs mess us up. So we like things without negative signs. All right. I guess I'm just admitting to a mild mathematical bias, but maybe I should say we like things who are less likely to make mistakes. All right, so these are the 4 you should know by heart. All right, let's do an example really quickly. Find the tangent line to y equals 6 tangent of x minus root 2 secant of x at x equals pi over 4, because we can find tangent lines of stuff. Now, if you're looking for a tangent line, what do you need? Right, so tangent line, remember, it's basically saying there's 2 things. What's the value of the function at the point, the value of the derivative at that point. If I want the tangent line, I need those 2 pieces of information. If I have the tangent line, I have those 2 pieces of information. So the f of a, that's getting into your point. Your f prime of a is getting into your slope. So let's do our point. And when I say f of a, our f of x is 6 tangent of x minus root 2 secant of x. All right, in the interest of time, I will help you with evaluating. F of pi fourths, 6 tangent pi fourths minus root 2 secant of pi fourths. I will tell you the value of one of these if you tell me the value of the other one. You get to go first. Which one of these 2 do you know? My heart, it hurts right now. There's tangent and there's a pi fourths. You should be like, oh, this is a great day for us. Tangent of pi fourths? 1. All right. 45-degree angle. Secant of pi fourths, square root of 2. If you're not sure why, cosine of pi fourths is 1 over square root of 2. Remember, secant is you flip cosine. Square root of 2 times square root of 2 is just a fancy way of saying 2. So you have 6 minus 2, which is 4. All right. Next, we are after the slope. What do you need to take the slope? Derivative. So our next step is, let's take a derivative. No problem. We're good at that. So the 6 just comes along for the ride. Derivative of tangent. Secant squared. Very good. Minus square root of 2, derivative of secant. Secant tangent. Great. All right. We're going to plug in pi fourths. So we're going to get 6 secant squared of pi fourths minus root 2 secant of pi fourths tangent of pi fourths. Now, I'm not going to tell you either of these values this time. You have to tell me. All right, secant squared of pi fourths. Do we know what that is? So secant squared of pi fourths is going to be 2. Because secant of pi fourths is root 2. It's that secret like, oh, what did we do before? Hey, it's the same thing. Okay, root 2 secant of pi fourths. Root 2 tangent of pi fourths. Tangent of pi fourths is 1. So this becomes 12 minus 2, which is 10. So y minus your y value, slope, x minus your x value. So this is your y minus f of a equals f prime of a times x minus a. Now, at this point, what do we need to do? We're done. That is a line, and it is the tangent line. Oh, how beautiful, how beautiful. We weren't asked to put it in a specific form, so that's good enough. All right, a minute left. Can you get this one? What is the smallest value of theta? So that f prime of theta is 0, where f of x is the function 2 sine of x plus x. Take the derivative of that function, set it equal to 0. When is the first time that you get 0? And by the way, f prime of theta equals 0, what does that tell you about your tangent line? If your derivative is 0, your tangent line is doing what? It's going flat, right? It's not going up, not going down. It's level. 0. So our options are pi over 6, pi over 4, pi over 3, pi over 2, and 2 pi over 3. The answer is E. Now you probably think like, how would we have known this? Let me point something out. Take the derivative, 2 cosine x plus 1, set it equal to 0. Cosine is negative 1/2. Cosine is positive in the first quadrant. All of the cosines were positive for these 4 choices here. So even if you only know that cosine is negative, the only option is E. So even if you don't know all of your trig values, you can eliminate. Multiple choice, half of the time you're faster just to eliminate options than actually find the correct option. All right, that's it for today.